So I will try a new technique. So last time we discussed the view overlap, open loop view overlap, and simply we said that if I can maintain the relation between the voltage and the frequency to be constant, then I will have the flux in the gap to be constant. Yeah? And of course, if I need to fix it, I will fix it where? At the rated conditions, which is the best conditions for what? For the machine. So this will be Vs rated over Fs rated. Yes? Yep. So last time we said that if I need to do implementation, the first thing here I will do is to specify the omega reference that I need to operate the machine. Then I will go to the curve, V over F curve. And last time we discussed that at low frequency, at low speed, I don't have sufficient voltage to ignore the drop voltage across the stator circuit, so I need to boost. I need to boost the voltage by delta. Or simply we said that we can specify two frequencies or two speed, the minimum and the maximum, which either related to the, let's say the frequency capability of the inverter, yeah? Or let's say the mechanical structure, the maximum speed of the machine. So let's assume that I'm specifying omega minimum and omega. So from the minimum omega min until omega rated, I will have what? I will follow what? The constant V over F control. Yeah. After that, I should fix the voltage. I cannot impose voltage more than the rated. Yes?
Okay.
Good. So this is instead that I will enter to where? To frequency control. So after omega rated or after F rated, if I need to increase the frequency above the rated, I should switch between constant V over F to where? To the frequency control. Yeah? So the output from this block is actually what? The amplitude of the voltage. Yes? It's amplitude. This amplitude can be a RMS value, can be maximum value, can be phase, can be line to line. In the end of the day, the relation between them is what is constant. So what I need only to know, this block will give me what? If this one was the maximum value, then in order to complete the reference, I need only theta. Yeah? We know that any sinusoidal signal is what? V max sine omega t, correct? So if this one is the maximum, I need only theta. If this one was the RMS value, I will multiply it by what? By square root of 2. Yes? If this one was line to line, I will divide it by what? Square root of 3. Yes? So let's assume that this one is what for me? The maximum value. I'm too old to write square root of 2. Okay. So if I need to complete the reference, I need the angle. The only information here I'm having is what? Is omega r. Yes? Here I'm discussing the open loop. I'm discussing here what? The open loop V over F. So here let's write. This one is the open loop V over F. So if open loop, this means that I don't have any measurement. Yes?
Yes.
So I don't have any information. So I will try to live with what? With the thing that I'm having, which is omega r star. I will assume that this one, if I integrate, I will get what? Theta. You know that the integration of omega is what? Is theta, d tau, and of course plus theta of 0. Let's assume this one is 0. So simply here, I will take this one here. Then I will integrate it. And for the integrator, this is what I will use for that. So this is an integration. So if I do the integration, I will get theta e, yeah? Which is omega t. Yeah? Which is omega. Now, I'm having what? I'm having magnitude and I'm having angle. Can I build the reference? Yes, I can build the reference. Yep. So here, عبد الله أجيت بعد غياب ها؟ اشتقنا لك الله يسلمك الله عليك نشرح لهم كل Okay. So here I will what? I will build the reference. Let's see, can I do it? Yes, sir? Yeah. So here is reference generation. Yeah? The reference generation. Now, for the reference generation, you know that, let's put it here. Huh? Let's make it 3 in 1. So VA as a reference will be what? مين؟ عمر؟ عمر. VA reference. مش مشكلة ما لهاش علاقة. If you are an electrical engineer, you can say that it's amplitude sine the angle. The amplitude that I'm having is what? This one. So this will be what? Vs sine theta. Yeah. Good. Now, in the end of the day, I will have 3-phase balance system shifted by 120 degree in space, correct? And the sequence is A, B, C. So this means that the B will be minus 120 degree, and VC will be what? Plus 120 degree, or minus the 240. Yep. So the same thing here, VB as a reference will equal Vs sine theta E minus. Here what I will put? 120 degree or 2 pi over 3? We don't care. It's just a number.
حسب الثيتا.
According to theta, this is the rad per second. This omega t, rad per second. So it necessitates I must add to it or subtract from it what? Rad per second. So it must be 2 pi over 3. But if I'm writing, I can write anything. If I need to implement it in Simulink, it should be what? Respect the unit. Huh? So I will respect that. So this will be what? 2 pi over 3. Huh? 2 pi over 3. And VC star will equal to what? يعني.
VS sine theta E plus 2 pi
or minus 4 pi.
The same, huh? Okay. Now after that, I'm having here what? I'm having references, 3 phase, 1, 2, and 3. This means that this line contains VA as a reference, VB as a reference, and VC as a reference, correct?
Yep.
Now, what I need to translate this control signal into a power signal. You know, this is a control signal. It cannot operate the machine by itself. It has low, it has what? Low power. It's impossible to feed the beast or feed the machine using this control signal. So I need what? Mechanism in between. So the mechanism in between is the inverter. But the inverter, unfortunately, is discrete component, correct? Switches, discrete. Can't understand analog signal. Only understand what? Digital. Close, open, 0 or 1. So what I need to translate those one to gate pulses. Good. So if I'm having, let's say, the reference, if I compare it to a carrier or triangular, then I will generate the gate pulse. Now let's see. If I'm assuming this is V star I, and I element of what?
A, B, C.
Yeah, of A, B, and C. So this means that either I'm generating the pulse for the leg A, which is the leg connected to phase A, the mean, or leg B, or leg C.
دكتور
مم.
ليش ما حطينا 3 triangle for each?
I'm too old. I'm trying to save ink. And short time. It's the same. Yeah? So simply this means that here I'm having 3 blocks actually. Yeah? The same thing. Yeah? So here I will generate what? If you remember last time, we said that the inverter had 3 legs. Yep. And if I'm assuming ideal switch, lossless switches, and this the leg of what? Of phase I, let's say, yeah? Let's be more than basit. Do you know basit? Oh. They're called Patrick, huh? Yes. Patrick. I like him. He's genius. Do you know why? Because he never uses his mind and his living. Imagine that he can use what? His mind. He's genius. Really is genius. So assembly here, if this phase I, so this will be the higher switch of phase I, and this will be the lower switch of phase I, correct? And you know that in general I'm having 3 legs connected in parallel. Yeah? So let's assume that this is the positive terminal and this is the negative terminal of the DC side. So here simply I will have what? I will have another 2 legs. So I need to generate what? The gate pulse for phase I, which is the A, the B, and the C. So if I compare, I will get what? The gate pulse for the upper switch of phase I. And you know that any leg, for any leg, this we call it leg, huh? Do you know, until now I don't know why they call it leg. Why they not call it hand? Yeah. Why? Why is not hand? Leg. This is a name, huh? إنما أسماء سميتموها أنتم وآباؤكم. So, if you know the answer, maybe. But for me, I don't know until now why they call it leg. Why not hand? No. Maybe leg, 3 letters. Hands, 4 letters. Maybe.
Kevin Ink.
So leg I, yeah? This will be a leg I. And we know that any leg, any number of switches in the leg must obey the summation of all the switches must be 1. Which be, otherwise I will do a short circuit. Yeah? So this means that what? I will have, for leg I will have the upper switch of the leg plus the lower switch of the leg getting signal must equal to what? 1. So if this is the case, someone will say that, okay, but invert, invert the signal. And this will be the gate pulse for the lower switch of the leg I. Good? Yes? So at the end of the day, the phase A, the phase B, the phase C will be connected toward the machine. The machine will rotate. At which speed? At a speed, hopefully, it will be close to omega R star. But it will never be. Why?
Open loop.
Why? You know that if you are a good mathematician and you can calculate, yeah, I can operate at the point I need, yeah, under the assumption I know the torque load, yeah. But here I cannot because the slip speed. I'm assuming now this speed is the synchronous speed, which is not. Correct?
Yes.
Yeah. Yeah. I need to operate at certain speed. I'm assuming that this speed is the synchronous, but it's not the synchronous speed. There's one omega slip in between. Yeah? Omega slip in between. So someone will say, what about if I can compensate of this omega slip? If I can compensate it, I can add it to omega R So I will generate what? The synchronous speed that the machine must rotate in order to what? To rotate at speed that I need to rotate at. Yes? Good. So now let's discuss with you the open loop slip compensator. Next one. سؤال؟ No.
انا بس سؤال بس لما حيرني ليش دائما نستعمل تراينجل؟ مش قادر يعني بس كثير
Now
حكاية.
this depend. This one will give you what? Symmetric
Oh.
wave bus. Now this depend on what? Depend on the reference. In general, the reference is the reference restricted between -1 and 1, or is the reference shifted to be between 0 and 1?
Oh.
Now, if -1 to 1, simply this one will be what symmetric in the positive and the negative half cycle. Yep. In the end of the day, you can use whatever you want. By the way, you can use sawtooth, but this one will generate less, let's say, switching losses. I can use square. In the end of the day, I will compare, correct? I will compare above or under, above or under. In terms of the harmonic pattern, this one is what? Is the best. And this one's symmetric, huh? The positive and the negative cycle are the same. The sawtooth, simply no, it's not. But the sawtooth can be used. Okay. So now we said that this one is open loop. So in general, we will have what? Error or mismatch. Due to what? Due to
Slip.
slip. Good. So this one not accurate enough. That's right here. Due to what? It's open loop. So due to omega slip. Yeah. So now, what about if we discuss the open loop V over F with slip compensation? I will try to compensate. And to pave the way for that, let's recall the torque of the machine. Do you remember the relation of the torque? It was 3. Yeah? P over 2 if I need to use the electrical synchronous speed. R dash over S omega S Vs squared over Rs plus R dash over S squared plus XLS plus XLR dash squared, and this one is already derived from the pair phase equivalent circuit, correct? Under the assumption that the drop voltage across the stator circuit here is negligible, so I can move this branch here. No? You assume that this one or delta Vs, let's say, almost equal to 0. Yeah? Good? Good. Okay. Now, if we need to maintain constant V over F, so at constant V over F, under the assumption that delta Vs is almost 0, then this means that E is almost equal to V, correct? Yeah? Good. So now, if we try to arrange this equation, and instead of the V over F is almost equal E over F, and this one is actually what? Or let's say here, we can multiply it by 2 pi here, so we can multiply here by 2 pi, so this would be E over omega S, correct? And this actually is indication for what? For the air gap and this one we need it to be what? Constant, correct? Yeah? So now let's try to arrange this equation. So simply TE, I can write it as 3 P over 2. Now instead of Vs, I will write E. So this will be E squared over, and instead of S, omega S, I will write it omega slip. You know that. Omega slip is equal to what? Yes, S omega S, correct? And I will end up with what? With R dash over. Now I will assume that the drop voltage after this circuit is almost zero. This means that RS is negligible and LS is negligible. So this one is out and this one is out, correct? And so this will be what? R dash over S square plus this one. Actually I can write it as omega S L R dash square, correct? You know that X is equal to what? Omega. Yeah? Yes? So here also if I multiply here by omega S, I can multiply here by omega S. Yes? So this will be omega slip. Yes? And this one here, I can get it out. Yeah? So I will get what? TE is almost equal 3 P over 2 E over omega S squared R dash over omega slip over, here I'm having R dash over omega slip squared plus L dash squared. Yes? What I did, the first thing here, I take omega S out, then I take this one here. Yeah? Yes? Yep.
دكتور شاي اوميجا سليب عند الاي اي
Where?
او
This one?
اللي تحت الار اوميجا سليب.
Yeah, omega slip. Yeah, I take it here. Good. Now you know that the inductance in general is what? It's very small. Yes? In millihenry. Square it will be negligible, correct? So in the end of the day, this means that the torque is almost equal 3 P over 2 E over omega is the gap, correct? The flux on the gap square, and this will be what? If I rearrange it, it will be 1 over R dash omega slip. Yep. Now those are constants, yes or no? They are constant. So this means that the torque is proportional with omega slip. Yes? The torque is what? Is proportional with omega slip. Yes? Sliman say, wait. Why you are doing all of that mathematics if you can prove it from the torque speed characteristic? Yeah? Yeah? So simply, maybe he say that, wait. This is the torque speed characteristic. Let's make it Ctrl Z. This one is working. No, I'm having it. This one is more convenient, by the way, than the PowerPoint. Yeah. So let's assume that this is the relation between the torque speed characteristics, so this omega and this. Yeah? Someone will say, see, if you are operating here, you are getting this torque, yeah? If you are operating here, you are getting this torque, yeah? Now at this point, you have this omega slip. At this point, you have this omega slip. If you are operating here, you will have this omega slip. So simply, this means that the torque is proportional with the omega slip. Correct? Yes? Yeah, but simply this is also a mathematical justification, and later on it will open the door to discuss what we call constant flux control. I will control the flux directly by controlling the current. Yeah? Until now, we are controlling the flux by controlling the voltage, the V over F, and maintaining the flux at a constant value by what? Regulating what? The voltage. Someone will say, well, if I can control the current directly, I can control the flux. It will be the same, but that one needs a current control. Until here, we are using what? Voltage. And in the end of the day, voltage is more straightforward to deal with. Good. So the torque is proportional with omega slab. ذكروني آخر ثلث ساعة عشان أعطيكم كويس. Do you remember the torque is proportional with what? With omega slab. So someone will say, omega slab rated, I can calculate. Yes, I can calculate. This one is proportional with TE rated. Correct? So simply, if I need to calculate any omega slip, which is proportional to any torque, I will say that omega slip will equal to what? Omega slip will equal TE over TE rated multiplied by what? By omega slip rated. Now, until here, I need to calculate this one. Now, this one we already know. From the nameplate machine, we can calculate. This one, we already know. Actually, this one is given. Because if I'm telling you that I'm having a machine that's rotating in 1375 RPM, then you will say it's 1500 minus 1375. This omega slip. Yep. Or any slip. It will be the same. It will be ratio. So it will be the same. So I need to calculate TE. Now, can I estimate TE? TE. If I recall, T is equal to what? Do you remember how we find expression for the electromechanical torque? It was the power on the air gap over omega s.
Yeah.
Yeah. If I still remember. So this one is equal to the power on the gap over omega s. Now the power on the gap is equal to what? Pn minus the P copper losses across the stator circuit. Some will say minus the power losses on the inverter. Yeah? Yeah?
Yeah.
So P inverter loss over omegas. But remember, the first time we met, I said to you, I'm not Dr. Mudaffar, I will deal with the switch as ideal switch, on or off. So this means that the converter is for me lossless. So this one can be what? Can be out. And I need to find a relation which approximates relation. So someone will say I can ignore this one. Yes. So in the end of the day, this will equal what? Pn over omegas. Now Pn is equal to what? Huh? But if I need VA or IA, this means that I need 3 sensors for the voltage, 3 sensors for the current, and I need the power factor. It will be very, very complicated. But simply under the assumption that I'm having lossless, so it will be VDC IDC. The power into the inverter is equal to the power out from the inverter, correct? And the power out from the inverter is the power input to the machine, correct? Yeah. Yes? So this will be what? VDC IDC. And in general, you know that this one's fixed. Huh? So I need only to what? To measure what? IDC. I only need to measure what? IDC. Okay. Over what? Over omega. And this one, omega s, yeah. Good. So now let's see if we need to plot the block diagram. So the first thing here, let us assume that we have here inductor, filter, and here I'm measuring the DC current. This is the I DC. Now this is the input to the inverter. If you need to measure the voltage, for example, also I can take it from here, and this will be VDC. Now, if I'm having VDC and I'm having IDC, I can calculate omega slip, yeah? Good? From this relation, yeah? So this will be slip compensation. So this will be what? VDC IDC over omega S over omega slip rated, yep, yep, multiplied by omega, oh no, T rated, huh? T rated. Over TE rated multiplied by omega slip rated. This relation, huh? So here what I'm getting, omega slip. Now this one I will add it to what? Omega R reference. So this will give me what? Omega S reference. So if I integrate it here, I will get what? Theta E, and here, if I'm using the V over F curve, what I will get? Vs. Now, after that, this should be the same as what? As the open loop V over F, correct? I'm generating a reference signal, I will compare it to a triangular, and after that, I will generate the get pulse for what? For the inverter, good? Yes? Now, someone will say, can you use a closed loop V over F? Yes, we can use. Now, this one need only a current sensor. If I need to use a closed loop V over F, I need taco generator, speed sensor. Yeah? And you know that measuring the current is easy, or let's say less expensive than the taco generator. Yeah? So now let's discuss the closed loop V over F.
دكتور اوميجا ريفرنس باللي قبل اللي هي السينكرونس سبيد.
Now this one will be the synchronous speed, yes?
لا اللي قبلها
No,
الأوميجا. هاي لا.
this one the actual speed that you need to rotate the machine.
The actual بنقارنها مع اوميجا سليب.
Plus.
بلس اوكي.
Now you know that omega
okay,
S is equal omega R plus
فكرت ماينس.
by the way, if there is no sign, by default,
بلس.
the summation, by default. If I need to subtract, I need to add minus. Without any indication of the sign, by default it's what?
Plus.
The plus. Okay. Good. Where is it? Next. So now let's discuss the closed loop V over F. Now someone will say, if this is the reference speed that you need to rotate the machine at, compare it to the actual reference now. Yep?
Yep.
So this is a minus, huh? And this will be omega. Then after that, you use what? A PI speed control. So KB plus KI over S. Yep. And do you remember when we said that the speed control, the output of the speed control is the torque, and the torque is the proportion with the slip. Yes?
Yes.
So the output of this control is omega slip. Correct? Yeah. Do you remember? I think in the second slide, we said that TE is proportional with omega slip. Yeah? So this actually is TE, but it's also what? Proportional to omega slip, so this will be omega slip. Now you know that in the control you have transients. Sometimes the signal can overshoot. In order to maintain stability, I will put this one to a slip limiter. Slip limiter. Logically, the machine cannot, the slip speed cannot be greater than the synchronous speed, for example. It can be. So in order to maintain the stability, let's say, here I will use what we call slip limiter. So this is a slip limiter. So this will be omega slip. That if we add to the omega r, we will get what? Yeah, omega s. Correct? Now this one will go to where? To the V over F control. Yeah? So the output is what? Is Vs. Yep. Now if I integrate this one, I will get what? Theta. Now this one coming from where? Yeah, from the package. Now after that here I will build the reference. 1, 2, 3. I will generate the gate pulse. 1, 2, 3, 4, 5, 6. This will be the inverter. This is the induction machine, and here we are using a taco generator for speed. Yep. And this is what we call the closed loop V over F. Yeah. Good. Do you have any questions here? Yeah? No question. Abdullah. Abadan.
بعد ال W سليب بالأخطاء حطينا سليب مش عارف شو
ليميتر
سليب ليميتر
Yeah. That's correct. Good. Okay. So now, if you don't have any question, let's discuss what we call constant air gap control. I will control the flux directly by controlling the current. Until now, the V over F, I'm controlling the flux or regulating the flux by controlling the voltage. Look, the reference is what? This voltage. Yeah? Okay. Now, if we recall, in order to have a constant flux, requires constant current. Do you remember, actually, when we drive the relation for the flux, we say the flux in the gap is equal the voltage across the gap over Xm, correct? Yeah. And this one is equal E over 2 pi F Lm, and this was Im. Yeah? This was Im, the magnetizing flux. Now, if I here multiply by Lm, then I will get what? I will get E over 2 by F. Yes? Yeah? Now, Lm in general constant. So if I need to maintain the flux constant, I need to maintain this current to be constant, yes?
Yes.
Right? But simply, I cannot control directly the current in the magnetizing path, can I? What I can control? The stator current. Yeah? I can control the stator current, and I know the relation. It's current division.
Yeah.
Yeah? So if I can build the relation between the IM, I can control the magnetizing current indirectly by controlling directly what? The stator. Yeah? So the constant flux requires constants IM, correct? Which cannot be controlled directly. This one we cannot control directly. So how to control it? By controlling what? IS. So by controlling IS, we can control what?
IM.
So now, if we recall the bare phase equivalent circuits, someone said that this one can be a representation for the impedance on the stator circuit. This one is the magnetizing inductance, and here I'm having what? The rotor inductance. ZR, ZM, and this will be here the current IS. And this current here will be what? IM. Huh? Now, what the relation between IM and IS? Current division, huh? You remember? Can you give it to me? Ismail. Dahab, can you give me IM in terms of IS? IM is equal over multiply by. You see, it's very simple. So it's ZR over ZM plus ZR multiplied by what? By IS. Yeah? So now let's substitute ZR by its value and Zm by its value. So simply, this one here. I was searching. So simply someone will say this will be IM will equal. Now ZR is actually J omega S L dash plus R dash over S over. Now I will add J omega S here, and this will be L dash plus Lm. Yeah? Plus R dash over S, all multiplied by what?
IS.
By IS. Good? Yeah? Good. Now, let's divide by R dash. If I divide by R dash and take omega S out, what I will get? So this will equal. Here I'm having J omega S, and this will be the R dash over R dash, and if I multiply here by S, I will get 1. Correct? Yes. The same thing I can do it, huh? The same thing, this will be J S omega S. Now this will be the R dash plus Lm over R dash plus 1. So let's fix this one here to be similar to that. So this will be J S omega S. سليمان
مش اس ار داش
وين هي؟
القسم اللي تحت
هاي؟
لا ال زائد ال على مش اخذنا اس عم نشترك مش بحسبها اس
I multiply above by S and down by S and divide above by R dash and down by R dash. Yeah? Yes? So this will be multiplied by what? IS. Yeah. Now let's see. In general, the rotor inductance equal to what? Any inductance equal to what in general? Any inductance is equal the leakage inductance plus the magnetizing inductance. Correct? Yes? So LR will equal to what? LLR plus LR. Yep? Yes? So LR dash, let's say. LLR dash plus LR. Yep? Now, tau in general equal to what? The time constant of any RL circuit is equal to L over R. So the time constant for the rotor circuit is LR over RR, correct? So the time constant for the rotor circuit is LR dash over RR dash. And let us define the following normalized inductance, which is the sigma R. Sigma R is equal to LLR dash over LR. Yeah? Now what I will do, the first thing, I will try to write IM in terms of IS. So I will switch those, correct? Yeah? So I will say that here I'm having what? IS is equal to what? J. Now instead of this one, I will put what? Omega slip. Omega slip. Now, do you see this one? This tau R actually. Yeah? So this will be tau R plus 1 over. Now, this one will be here, the denominator. So this will be J omega slip. Now, this one actually will equal sigma R over 1 plus sigma R multiplied by tau R. Yeah? So this will be what? Sigma R over 1 plus sigma R multiplied by tau R plus 1. And if I multiply it by what here? By I. Now let's see. This relation depends on what? What's the variable here? IM is variable or constant? Constant. So LM is constant. R is constant. The inductance is constant. The resistance is constant, which means that tau R is constant, sigma R is constant. So this is a relation between omega slip and the amplitude of the stator current, correct? Yeah? So simply this means that because this one is constant actually, at which value? At the rated value. Yeah? At the rated value, صح؟ ها؟ ما نمشي امبارح؟ ايه ما شاء الله. يلا ماشي. So constant, I am constant from the what? From the rated condition. Which means that now if I'm having omega slip, if I'm having the relation, I can plot this relation, or I'm having the relation, yeah? You know, this one is what? Has magnitude and angle. Yeah. So the magnitude will give me what? The relation that I need. So here I will take what? The magnitude of the stator. Yeah? And if I'm having omega slip, if I add it to omega R, I will get what? Omega. So now, instead of building a reference voltage, I'm building what? Reference current. Yes? Yes? Okay. So let's do it here. Plus 1. So the same thing here, let's do the step control. So the first thing here, I'm having omega R start. I will compare it with the actual omega R. Then I'm using a BI control, which is KP plus KI over S. Then I'm having a limiter. Then I will have a limiter. So this will be omega what?
Omega slip.
Omega slip. Now this omega slip will go to the constant flux relation, and I will get from it what? IS as amplitude. Now this one here, if I add it to omega r, I will get what?
Synchronous.
Omega s. If I integrate it,
You get
I will get what? Theta. Now I will build what? The current reference. So here I will build it. So let's build it here. So now what I'm having, I will have IA as a reference. This will equal to what? Who can give it to me?
IS.
Now, we assume that this amplitude is the maximum. You know that in the circuit analysis, either you are using the maximum value or the RMS value. Yeah? This according to the textbook you are following or to your instructor. From the day one, he will say to you that I'm using the RMS value. Yeah? Or I'm using the maximum value. Yes? So let's assume that we are calculating the maximum value. Yep. This is from the phasor relation. Yeah? So IS sine theta. IB will be shifted by 120 degrees and so on. Huh? So we should write here IB star equal to what? IS sine theta minus 2 pi over 3 and so on. Huh? And so on. Now after that, I need to generate the gate pulse for the inverter. How I can do that? اسمع. نورس عبادات؟
لا قرآن.
مين نورس عبادات؟ ذاكرينه؟ نورس عبادات بيلعب معك كفر السحب هو عنده شوية مصاري. لقى نفسه he found himself in a boy. منطقيا if you calculate this is a good business man.
Yes.
Maybe one of the what? Real Madrid or Arsenal. No. I know it. Quran. Again. I need to generate the gate pulses for the inverter. How I can do that? Okay. I need a current control. In the day one, I need a current control. Yeah? Because this is what? Reference. Yeah? In the pulse width modulation, the pulse width modulation will force the inverter to operate at my reference. Yeah? I'm generating gate pulse according to my reference. Here I'm having current. So I need in the first stage what current controller to tell what? The inverter to operate at the current I need. Huh? So if we go 2 steps back, do you remember the DC drive, the Chubar control DC drive? In the current control we have either hysteresis current control or pulse PI plus the PI plus pulse width modulation. But simply you know that the PI control is most powerful when the reference is constant. If the constant is alternating, it will be what? Yeah, like SpongeBob. It will do nothing. Yeah. So simply this will shrink the options to what? To the hysteresis current control. Yeah. So I need to do current control, which will be hysteresis current control. So this will be what? Hysteresis current control.
ما فهمتش ليه احنا قلنا مش الفيكس احسن من البي اي ولا البي اي اي مش فيكس
Just a minute. Current. And here controller يا قرآن نساوي. Now, we was discussing that the BI control is most powerful when the reference is constant. But here the current is alternating. So simply
حتى
ما سمعت قاعد أجاوب سؤال.
حتى الريفرنس معنا جنريشن برضه.
It's a sinusoidal signal. It must be a sinusoidal signal. Yeah? So simply this means that I will do what? Hysteresis current. Yeah? And the hysteresis current control go 3 steps back to the DC drive and refer to the lecture when we discuss what? The hysteresis current control implementation.
دكتور ممكن قبل ما نبلش الكويز بس